Flip a fair coin repeatedly until a head appears. Let the random variable x be the number of flips required. Find the probability mass function of x, and the probability x is an element of the set A, where A is the set of all x such that x equals 4, 5, 6, 7, etc. So the first step is to find the probability mass function f of x. And in this particular case, it might take one flip to get the first head. It might take two flips. It might take three flips. And there's really no upper bound that you can put on the number of flips required, because as soon as you think of a large number, like say 37, then it's possible that it takes 38 flips to get the first head, and so there's no limit here. It goes forever. This is the first case that we've seen where we have a support that is a denumerable set. In the previous 7 examples, all of the supports have been finite sets. In this case, it's denumerable. What is the probability that it will only take one flip to get the first head? That should be a 1/2. What is the probability it will take two flips? Well, that would be a tail followed by a head, and that probability is 1/4, etc. So this probability mass function is 1/2 raised to the x power. In order to find the probability x being in the set A, where A is 4, 5, 6, etc., that's the same as saying the probability x is greater than or equal to 4, and that is f of 4 plus f of 5 plus f of 6, etc. F of 4 is 1/2 raised to the 4th power. F of 5 is 1/2 raised to the 5th power, etc. If you factor a 1/2 raised to the 4th power out of every term, you will get 1 plus 1/2 plus 1/2 squared, etc. And you recognize that as a geometric series. And you know that the sum of the geometric series 1 plus r squared is 1 over 1 minus r whenever the absolute value of r is less than 1. So this turns out to be 1/2 times 1 over 1 minus the common ratio, and the common ratio is 1/2. So that turns out to be 1/2, oops, I forgot the 4th power here, 1/2 to the 4th power multiplied by 2, and that is 1/2 cubed, which is 1/8. Now on the next page, I plot the probability mass function, but in this case I only plot it for the first 8 mass values. This probability mass function goes all the way out to infinity, but I just show the first 8 probability mass function values. F in this case is 1/2 raised to the x power, and when you make the plot, it has this classic shape to it. This turns out to be a special case of a distribution that we'll encounter in the next chapter that's known as the geometric distribution. If we were a little bit nervous about our calculations here on getting 1/8 as the probability of x being greater than or equal to 4, we can run a Monte Carlo simulation to check it. And here is the code. First of all, we're going to have 100,000 replications. We're going to have a counter which counts the number of times that we get an x value greater than or equal to 4, and we initialize that counter to 0. Then we have a for loop which goes from 1 to 100,000. And the first thing you do is you set x to 1. That's kind of the default value. And then there's a while loop. And while you get a uniform 0, 1 that is less than 0.5, that is modeling a coin flip, So while you get a tail, you simply go ahead and increment x equals x plus 1. And then the last statement is if x turns out to be greater than or equal to 4 coming out of that while loop, then you increment the count. You end the for loop, and finally at the end here you print the ratio of count to nrep. I ran that 5 times, and here are the results. I got 0.12527, 12505, 12531, 12384, and then 12535. These values hover around the analytic value of the probability that x is greater than or equal to 4 is 1/8, which is 0.125, and because they hover around that particular value, this Monte Carlo supports the analytic result.